In this trial, Sarah and Aiden are running towards each other, and each have an initial velocity. Sarah is running in the positive direction, and Aiden is running in the negative direction. Since we know that the initial momentum and the final momentum are both the same, we can solve for the final velocity of Sarah after the collision. So we can set up our math right now. P1 equals P2. The mass of Aiden times the velocity of Aiden plus the mass of Sarah times the velocity of Sarah, initial, equals the mass of Aiden times the final velocity of Aiden plus the mass of Sarah times the velocity of Sarah. So we're plugging our values, and remember that we're solving for the final velocity of Sarah, so we'll make that value x. And then do the math. And the final velocity of Sarah after the collision is 0.93 meters per second.
Humans were so hard.
Yeah, ready?
Humans were so hard.
Yeah, ready? In this trial, Aiden is standing still and Morgan is running towards him with initial velocity. Now, initially Aiden doesn't have any momentum because he is standing still. However, after the collision, some of the momentum that Morgan has is transferred over to Aiden. But just like the law of conservation of momentum says that the initial momentum equals the final momentum, and we can solve for the initial velocity with which Morgan was running at and collided with Aiden. So we can set up our equation, P1 equals P2, mass of Morgan times the initial velocity of Morgan, plus the mass of Aiden times 0, which because Aiden isn't moving, equals mass of Morgan times her final velocity, which is negative 0.8, plus the mass of Aiden, which is 87, times negative 0.5, his final velocity. So set up our equation and solve for the initial velocity of Morgan, which is negative 1.5 meters per second. We can also use the law of conservation of momentum to find the person's mass. So in this trial, Sarah is running towards Morgan while Morgan is standing still. Remember that the initial momentum equals the final momentum, and we can help solve for the mass of Sarah. So the mass of Morgan times the initial velocity of Morgan, which is 0 because she's not moving, plus the mass of Sarah times the initial velocity of Sarah, which her initial velocity is 1.5, we're solving for her mass, equals the mass of Morgan times the final velocity of Morgan plus the mass of Sarah times the final velocity of Sarah. So we plug in our values and we're solving for x, which is the mass of Sarah. And then move your x's to one side and then solve for x, and you should get your final mass.
Ready, go. I'm
Here we go.
Ready? Go.
Okay.
We'll just it'll be natural.
Rolling.
Yeah, we'll make it natural. Hello, and welcome to physics in your backyard. We are going to teach you how to do center of momentum practice. Hello, and welcome to.
Sorry. Action.
Y'all ready?
Oh, like cold hair? I don't even like lock elbows.
Yes, go ahead. Hello, and welcome to Physics You Can Do at Home. We're going to teach you how to do center of momentum using yoga balls and a couple of your friends. And first we're going to explain what center of momentum is, and then we're going to show you how you can do demonstrations to show how center of momentum works, and we're also going to show the science behind it. Don't mind them, they're just acting silly. So, what it and on the way we might get brain injuries, but it's okay. So, was that good?
It doesn't work.
Oh, I did it! I did it!
Do it now.
Yeah, see?
Perfect. Oh, well, we saw.
Okay.
Oh wait.
Anyway.
Please nothing happened. And we're going to go bring it around town. Around town.
Stop on your right foot. Don't
Stop on
forget
your
it.
right foot, don't forget.
And double take 3 times. 1, 2, 3. And pelvic thrust. Woo!
Stop on your right foot. Don't forget it. Now it's time to bring it around town. Bring it around town. Then you do this, and this, and this, and that, and this, and that, and this, and that, and this, and that, and then.
That's like doo-doo.
It's an elephant, or it's a giraffe. It's a giraffe.
All these kinds of places make it seem like it's been ages. And tomorrow's